you hear me? It's okay?
Yes, perfect.
Okay. So neurogeometry concerns integrative and functional neurosciences, and it works at the mesoscopic level and does not directly concern the ODEs of neurons or PDEs of neural networks. Its purpose is rather to understand the cortical implementation, the possibility of a cortical implementation of the global geometry of visual percepts as resulting from an integration process of retinal very local differential sense data. And this purpose comes up against a hard problem. The geometry of visual perception involves many differential computations, it's evident. But neurons are essentially point-like processors. They can only code a single numerical value by means of their firing rate. Of course, they are connected and they can transmit their activity along their more or less inhibitory or excitatory connections, but this is radically insufficient to directly implement differential routines. There is therefore a sort of antinomy at the root of a neurally implemented perceptual geometry, how differential routines can be neurally implemented in networks of point-like processors, since derivatives are not point-like entities. Now, it is a key empirical fact that biological evolution has introduced new post-retinal neural modules and neural layers, such as lateral geniculate body, cortical layers, orientation hypercolons, etc., that implement new variables, new post-retinal variables, beyond variables of retinal position. And so we can therefore try to understand how a connectivity, a neural connectivity extended to these new modules and new layers can perform differential computations. Of course, it must certainly have a very, very special functional architecture. But we must also know at the mathematical level under what conditions a point-like functional architecture is able to implement differential calculus. So the hypothesis of neurogeometry is therefore that maybe point-like processors can implement an alternative formulation of differential calculus using what Richard Montgomery called hidden derivatives as new supplementary independent variables, which can be in a second time implemented in point-like processors and interpreted as true derivatives. So these new hidden derivatives must satisfy strong, very strong constraints in order to be interpretable as true derivatives. And for that, the connectivity of the network must be extremely specific. Now, alternative versions of differential calculus do exist in modern differential geometry, since it is a very important and very old tradition. Jacobi, Frobenius, Lie, Darboux, Cartan, Weil, Goursat, etc. And it is these alternative versions of differential calculus which perhaps can solve the hard problem. And to understand why, we have to dive deep into the history of differential geometry. And for some slides, I will speak on the history of differential geometry. The geometrization of the integrability conditions of differential equations have been a revolution very similar to that accomplished by Galois for the resolution of algebraic equations. For a long time, the problem of the integration of differential equations, such as the sum of ai dxy equals 0, was considered as impossible, absurd, meaningless, as it was said at the time, if there was no integrating factor. And Gaspard Monge was one of the first to explain that, he worked in dimension 3, the conditions of integrability means that the solution of omega equals 0 are surfaces in R3, but that when the conditions of integrability are not satisfied, there still exist solutions, but which are one-dimensional skew curves and no longer two-dimensional surfaces. And it was a very a true revolution, this extension of the concept of solution. And from Pfaff to Frobenius, differential geometers had gradually understood the very deep condition of integrability. Omega is a one form, wedge d omega is a differential of omega, equal 0. Monge raised what became 30 years later the Pfaff problem, the well-known Pfaff problem, and he prophesied its importance. Quotation, it was not noticed that this was the beginning of an immense chain to which lay the great difficulties of differential calculus. And from that turning point, from that moment, geometrizing the integrability of differential equations became the problem of analyzing tangent hyperplane fields, kernels of differential one forms, contact forms, etc., etc. And so the basic notion became, at that time, that of a contact element. It was Lee's Fleschen element, that is a pair of a point x of a manifold and a hyperplane kx of the tangent plane of M at x. And as you know, Sophie Lee developed it in great detail with a strong sense of the inversion of point of view it brought. And in a beautiful text of 1894, the geometric work of Sophie Lee, Felix Klein emphasized the importance of the change of perspective brought about with this new, clear, and penetrating view, as he said. He explains that Lee introduced new elements of space, much more general than points, and instead of applying the methods of differential analysis to geometry, was interested in the reciprocal and developed the application of geometrical intuition to analysis. And this is the key foundational issue, exactly as in Galois for algebraic equations. The essence of differential calculus shifts from analysis to geometry. And so we can see now why and how point-like processors can be good differential geometers if they are able to detect contact elements. And in the 90s, I developed the following relations between this type of geometry, Pfaffian geometry, and neurophysiology. First, a class of cortical neurons in V1 called simple neurons detect contact elements AP, where A are positions on the retina, and P, a local orientation at A. It was the work of the Nobel Prizes Hubel and Wiesel. The vibration AP over A, with fibers, the projective line of orientations, is neurophysiologically implemented by retinotopy and orientation hypercolons. Third, the contact structures of the one jets of plane curves is neurophysiologically implemented by horizontal cortical connections. And fourth, the sub-Riemannian geometry of this contact structure is neurophysiologically implemented. In particular, illusory contours can be interpreted as a geodesics. So you see that it is exactly as in general relativity. You need a deeper concept of geometry, Riemannian geometry, to understand how inertial motions of planets can be at the same time very, very complex motions, because the space is curved, is a Riemannian manifold. Here it is exactly the same. You can understand how activated neurons can do differential geometry if they implement contact elements and contact structures of contact elements. But directly, you cannot understand how neurons can integrate partial differential equations and ordinary differential equations. By the way, long-range illusory contours are one of the most striking phenomena of low-level vision. For instance, we can reconstruct the shape, and it is a well-known example of a Dalmatian dog in this very incomplete image. And we will see that they can be interpreted as geodesics of a contact structure for an appropriate metric. And such sub-Riemannian models generalize the previous model due to David Mumford and based on the theory of elastica. And they have many applications, in particular for inpainting, since to complete a corrupted image, we must construct the illusory level sets that can complete the missing parts. And the following picture shows how a highly corrupted image at the left can be very well restored using sub-Riemannian diffusion. It is Gautier Prandtl painting, and the face of our friend Jean-Paul appears out of the blue. So, simple neurons of V1 are parameterized by triple AP, where A, X, Y is a position on the retina identified with R2, and P is an orientation modulo pi at A. And so simple cells of V1 constitute a field of orientations, and this field is the basis of the functional architecture of V1. What could be its structure? The first global reconstruction of an orientation field from the sparse local data provided by electrodes, still Hubel and Wiesel works, was inferred abductively in 1979 by Valentino and Carla Braitenberg. And this was long before the introduction of modern in vivo optical imaging techniques. And after Braitenberg, in an astonishing paper of 1987, still before the advent of optical imaging techniques, Nicholas Swindale reconstructed the spatial layout of the orientation map, what are now called pinwheels, and he thus confirmed Braitenberg's abduction. Here you have a reconstructed field of orientation by Swindale, and using a color code for directions, he got an orientation map. I insist and I emphasize the fact that this is a theoretical reconstruction and not at this time an empirical observation. But as you know, Braitenberg's and Swindale's abduction have been strikingly confirmed in the 90s by brain imagery, and you all know orientation maps with pinwheels. Here it is the V1 area of a macaque by Blasdell and Salama. Okay, now geometrically, pinwheels can be interpreted as blowing up of points AI, and the orientation field is the closure of a section of the fiber bundle VG, G for jets, equal R2 cross P1 over R2, defined over the open subsets R2 minus the point AI, the blown up points AI. Over the AI, the closure of the section sigma is the exceptional fiber P1, and these exceptional fibers P1 are contracted and folded onto small neighborhoods of the base points AI to give pinwheels. So there is therefore a 3D to 2D, two-dimensional collapse. An orientation map is in a way a geometric object of intermediate dimension between 2 and 3. And at the limit, when all the points of the base plane R2 are blown up in parallel, we get the fiber bundle VG R2 cross P1 over R2. And so VG can be considered as an idealized continuous model of the concrete neural V1 produced by biological evolution with its pinwheels and orientation fields. But the vibration VG R2 cross P1 over R2 is not sufficient for interpreting P as hidden derivative, in the sense of Richard Montgomery. That is, as a tangent to a curve. For that, P must satisfy the fundamental Pfaff equation, omega equal dy minus p dx equal 0, defining the contact structure of one jets of plane curves. As you know, a curve, a skew curve in VG is a Legendrian lift of its projection onto the base plane R2, if and only if it is an integral curve of the contact structure. Now, let's remember that the contact structure is left invariant for a group law, making VG isomorphic to the polarized Heisenberg group with its well-known Lie algebra. VG is an nilpotent group of step 2, Carnot group, and you can generalize to the Euclidean group SE2. The contact form of SE2 is cosinus theta dy minus sinus theta dx. The contact planes are spanned by the tangent vectors x1 cosinus theta dx, sinus theta dy, and x2 equal d theta, with Lie bracket sinus theta dx minus cosinus theta dy. It is essentially the red vector. And the xg constitute an Euclidean orthonormal basis, and the distribution C of contact planes is still bracket generating, but SE2 is no longer nilpotent, and the Carnot group VG, the polarized Heisenberg group, is its tangent cone, its nilpotentization. Now, the very key point for the neurophysiological level, which is another striking experimental discovery, is that the contact structure of V is implemented in a specific class of neural connections. Orientation hypercolons correspond to the vertical retinogeniculocortical connectivity, but cortical neurons of V1 are also connected by horizontal cortico-cortical connections inside the cortical layer itself. And such a second system of long-range horizontal cortico-cortical connections is necessary to implement a parallel transport, enabling the visual system to compare two retinotopically neighboring orientations, hypercolons P and PB, over two different base points A and B. Here is a quotation of William Bosking, an eminent specialist of these questions. The system of long-range horizontal connections can be summarized as preferentially linking neurons with co-oriented, co-axially aligned receptive fields. This means that the chain of simple neurons EI, PI is a chain of horizontally connected simple neurons, if and only if it is a discretization of the Legendrian lift of a not too curved base curve interpolating between the AI. And so this means that up to some bound and curvature, the contact structure C is neurally implemented, neurophysiologically implemented in V1. Okay, and now in the last part of my talk, I will come back to curved illusory contours. Variational models have been introduced since the late 70s. They minimize an energy along curves in the base plane, and the best known is the Elastica model proposed in '92 by David Mumford. But for neural models, and not only 2D image processing, it is natural to work in V1 with its contact structure and the Legendrian lifts. And it is here that sub-Riemannian geometry fully comes on stage. The natural idea is to introduce sub-Riemannian metrics on V and look at geodesics models for curve completion and illusory model contour. The sub-Riemannian geometry, as you know, of the Heisenberg group has been explained in the 80s by Richard Beals, Bernard Gaveau, and Peter Kreiner, and it can easily be adapted to the polarized Heisenberg group. And geodesics are projections of the trajectories of a Hamiltonian field of the cotangent space, and using variables associated to the length of the geodesics and the initial conditions, the covector, the initial covector, the sphere centered at the origin and with radius r, and the wavefront W of H are given by the following equations, where theta is the angle of the tangent. And of course, it is the modulus sine phi over phi, which is very important and explains the strange geometry of the sphere and the wavefront. They are displayed in the following figure, and such a complex behavior is impossible in Riemannian geometry. Here is a sub-Riemannian sphere, and here is a view, an internal view of the wavefront, with the y-axis, which is a degenerate caustic, singularities on the y-axis, and smaller and smaller circles of cusp singularities which converge to zero. And the following figure displays the distribution of the cusps of the wavefront. Okay. And now my last slides are on the geometry of SE2. With Giovanna Sciti and Alessandro Sarti, we studied the passage from the VG bundle with its natural action of the Euclidean group, R2 cross S1, to its associated principal bundle. And we thus go to the model I call the VS, equal SE2 endowed with its natural contact structure and its associated L-invariant sub-Riemannian metric. And the geometry of the sub-Riemannian spheres and wavefronts is much more complicated, and it was computed essentially by Andrei Agrachev and by his team, Yuri Sashkov, Hugo Boscain, Moyesev, Jean-Paul Gaultier, and others. If the lambda I are the components of the covector lambda in the basis omega I dual to the basis xi, the Hamiltonian giving the geodesics is half the sum of the square of lambda 1 and lambda 2. And if h is constant, and if we make the change of variable lambda 1 equals sine of half gamma and lambda 2 minus cosine of half gamma, then gamma satisfies the pendulum equation. And the Hamilton equations are given in function of theta and gamma by the following equations. And so you have a pendulum in the cotangent space which control the behavior of the geodesics. The phase portrait of the pendulum is stratified, and its stratification governs the classification of geodesics. Here is a phase portrait. In magenta, you have the open strata of oscillating motions. In yellow, the rotating motions, and in thick lines, the stratum C3 between the strata C1 and the strata C2, and also point strata, which correspond to the stable and unstable equilibrium. And Sashkov computed all the sub-Riemannian geometry of SE2 using Jacobi coordinates phi and k, which rectify the dynamics of the pendulum gamma. And in these coordinates, the vertical system in the fibers become trivial because k is constant and phi is linear. And k is the modulus of the elliptic integral associated with the pendulum. It encodes the energy of the pendulum, and phi is the pendular time length. It encodes the length of the geodesics. And for instance, for the C1 stratum, oscillating pendulum, Moyesev and Sashkov found the following equation with the Jacobi Sn, Cn, and Dn elliptic function. So we have this formula and explicit formula, and we have similar formulas for the other strata. The sub-Riemannian spheres and wavefronts look a bit like those of the polarized Heisenberg group, but are much more complicated. The fundamental difference is that the y-axis, which was a degenerate caustic in the VG case, splits into 4 branches and an asteroid surface, and the point singularity on it unfolds into small, what I call tetrapaks. We illustrate the case for the radius half pi. The strata Ci are sent by the exponential map into strata WCi, and the following figure displays WC1, the oscillating part of the pendulum, and the C3, WC3, the image by the exponential map of the C3 intermediary strata. So here it is in some sort the half of the sub-Riemannian sphere. But the most complex part of the sub-Riemannian sphere and wavefront is given by the images of the C2 strata with an infinity of singularities accumulating at the origin. So here you have the image of some level lines of WC2 plus, for k equal constant, the modulus k equal constant. And so you see these level lines. Here you have another image, more complete image. Now, in the formula for the strata C1 and C2, the Jacobi elliptic function have period T1 equal 4k of cap k of small k, k is the modulus, and cap k is the complete elliptic integral of the second kind. Yes. And T2, the period for C2 is 4 small k cap k. For C1, you can have a solution of the equation period equals the radius, to take the radius equal to the period, only if t is greater than 2 pi. But for C2, and it is the origin of the complexity, there exists always a solution kr of the equation r equal the period 4k cap k. And for this value, we get exceptional level lines. And for periodicity of the elliptic function Sn and Dn, and the fact that Dn has period 2 cap k, while Sn has only period 4 cap k, the exceptional line LKR is degenerate. I make some pictures. So the value of k for half pi is this value. You have a degenerate level line, but very close to this degenerate level line, you have another degenerate level line. You see the value. For k half pi c, c for critical, you have another degenerate level line, and the surface of the wavefront has an envelope between these two degenerate level lines. And the surface of the wavefront between these two degenerate level lines has a form of a sort of tetrapak, as in the figure. Here you have an image of the surface of the wavefront, where you see in the middle the tetrapak and the rest of the surface at the exterior of the interval corresponding to the tetrapak. And when the radius r varies, the ends of the two degenerate level lines, LKR and LKR critical, run along 4 branches, which splits the degenerate y-axis of the case of the Heisenberg group. And it is my next slide. It displays the sphere and the wavefront of the SE2 Riemannian geometry. So here you see how the C1 strata and the C2 strata are glued together by the intermediary of the C3 strata. And here is another perspective. And by transparencies, you see, as in the Heisenberg group, the circles of cusps converging to the origin. Okay, and so we see that the sub-Riemannian geometry of a Lie group as elementary as SE2 is rather complex. And so my conclusion is that we need this type of geometry, contact geometry, sub-Riemannian metrics of contact structure to understand how the visual system is able to do sophisticated differential geometry with only point-like processors. The philosophical key is that you can implement in point-like processors contact elements and connections between contact elements, even if with neurons you cannot directly solve differential equations. Okay, I hope it was not too long. No, it's okay.
It was a couple of minutes, but thank you very much. It was excellent hearing your talk and all about your view. Maybe one quick question. Does anyone have a quick question?
I have a small question.
Yeah.
Thanks a lot for this enlightening talk. My question is that intuitively I'm always confused when we talk about the need of endowing these point processes, the neural activities being point processes with a certain notion of differentiability. Could we say that the motivation behind this need, this effort, is to try to think neural activity within a context of neural connectivity? And if not, what is the real motivation behind this effort of try to endow the neural activities, I mean, these point processes with a notion of differentiability?
Yeah, how to say? It is exactly as the problem of general relativity. Take classical mechanics. You have empirically complex motions of planets. With Newton, Lagrange, etc., you have fantastic differential equations modeling these very complex motions, okay? Now there is a philosophical problem. Planets cannot compute differential equations. Physically, the only thing that can do planets is to have inertial motions, to be inertial, okay? So you have to understand how inertial motions can be complicated and not only linear motions, as for the Galilean group. And for this, you have to completely change and complexify the geometry. Yeah? And it was general relativity. In general relativity, the motions are purely inertial. So the planets have nothing to do. The complexity is in the geometry. Okay. For the differential geometry of vision, you have the same thing. This differential geometry must be implemented in neurons. But neurons cannot do differential equations. They cannot compute. The only thing they can do is to be activate and propagate activation along connections. This is the equivalent of inertial motions. They do nothing. They are activated by the inputs and propagate. So all the job must be done by the connectivity. So you have to understand how a connectivity of point-like processors, which has only a capacity, the capacity of being activated, can do the job. And for this, you need a geometrization of differential calculus. And the origin of neurogeometry is the discovery that at the retinal level, you have only points. And if you want to compute a tangent of to a curve, you have to do classical differential calculus. But biological evolution invented cortical layers with orientation, with neurons able to detect orientations. And so you can detect with a point-like processor of a higher level produced by evolution, but far beyond retina. It is sophisticated cortical layers which do the job. You can implement hidden derivatives. Okay. And it is because there is this implementation of hidden derivatives that the cortex can do differential geometry.
Okay.
And so you have to use, in the same sense as Riemannian revolution is absolutely necessary to general relativity, my hypothesis is that contact geometry, invented by Monge, Pfaff, etc., Frobenius, Cartan, Goursat, etc., is necessary to interpret the neural implementation of perceptual differential geometry.
Okay. Okay, thank you. Thank you very much.
So, thank you very much